practice problem for you. What's the percentage of oxygen in the air that you breathe every day? Hopefully you answered 21%, or to be more precise, it's about 20.9%. And this is an important number you'll need to know. You're also going to need to know the percent of nitrogen in the air and the percent of carbon dioxide in the air. Now let's see who's paying attention. What's the atmospheric pressure at sea level? I've mentioned this number several times already. Hopefully you answered 760 millimeters of mercury. This is a number that you should commit to memory and that you should know. Now, before we can discuss how gases diffuse, both in the lungs as well as in the tissues, we have to do some quick review of the partial pressures of gases. And we have a law for the partial pressures of gases, which is called Dalton's law of partial pressures. And that was developed by John Dalton, who was an English chemist, physicist, and meteorologist. Dalton's law is quite simple. It just says that the total pressure of a gas mixture is equal to the sum of all the pressures that each gas would exert independently. So another question you might have right now is, how do you calculate the pressure of a gas? When we calculate the pressure of the gas, it's the force that the gas exerts on the walls of the container that it's in when it's being measured. This is a nice visual representation of the partial pressures of gases. So we have three different gases here, and they each have their own partial pressure, right? So that's the pressure that they exist in the volume that they are existing in. So it's going to be based on the number of molecules and the properties of those molecules. So in this description, or in this picture, it kind of looks like all three molecules kind of have a similar percentage. And so in this case, we're just going to assume they might all be similar in properties as well as percentage. So maybe the partial pressure of gas A is 100, the partial pressure of gas B is 100, and the partial pressure of gas C is 100. If I put them all together, the total pressure here would be 300 millimeters of mercury if each had a partial pressure of 100. Now, when we're concerned with partial pressures, we're often concerned with what is the partial pressure at a given elevation. And if you're on Earth and you're at sea level, that corresponds to our barometric pressure of 760 millimeters of mercury. And barometric pressure is just another way to say the atmospheric pressure. So that will change as you change in altitude. Barometric pressure is very closely approximated by the hydrostatic pressure that is caused by the weight of air above the point that you're measuring. So as the elevation would increase, so you're going high up a mountain, for example, there's less overlying atmospheric mass. So that atmospheric pressure decreases as we go up in elevation. And you might be wondering, well, why is that important? Well, it's important because when we go to calculate the partial pressures of gases, we take into account what is the barometric pressure. So we know that in Earth's air, that we have roughly 20.93% oxygen, 0.03% carbon dioxide, and 79% nitrogen. So if I wanted to calculate the partial pressures of each of those gases, I would convert those percentages into decimal form, and then I would multiply by the barometric pressure. So for example, I would take 0.2093 multiplied by 760 millimeters of mercury, and I would be calculating the partial pressure of oxygen, which would be 159 millimeters of mercury. And that's important because our gases are going to flow from a high pressure to a low pressure. So in my tissues, the partial pressure of oxygen is much lower. That's going to facilitate moving oxygen into my tissues. I've got this nice big gradient. Well, if my barometric pressure goes down because I'm higher in elevation, I'm standing on top of a mountain, my partial pressure for oxygen would be less. So I've compressed the partial pressure gradient, so oxygen isn't going to want to move from the atmosphere into my tissues at the same intensity as it would if I were at sea level with a barometric pressure of 760 millimeters of mercury. Now in real life, we're thinking about primarily oxygen and nitrogen and how they contribute to the total pressure or atmospheric pressure. Now you could lump in carbon dioxide here, but it does play a very small role. So if we just focus on our nitrogen and our carbon dioxide, well, in that case, one is just shy of 21%, which is our oxygen, and the other is just shy of 79% or 78%, which is our nitrogen. So they're really making up the bulk of that 760 millimeters of mercury. So if I wanted to calculate the partial pressure of each of these gases, I would take 760 millimeters of mercury, and for oxygen, I would multiply by 20.9, and I should get roughly 159 millimeters of mercury. Now, if I do that same thing with nitrogen, I'm going to take 760 millimeters of mercury for nitrogen, and I'm going to multiply it by 0.79, the percentage of nitrogen in the air. And I'm going to get roughly 593 millimeters of mercury for the partial pressure of nitrogen. And these are the two gases that make up most of the gas that's in the air, and these are the two that we probably pay attention to the most, at least when we're thinking about what's contributing to the total pressure. So many of you have maybe hiked Clingman's Dome, which is a very common or popular hiking spot here in East Tennessee. So Clingman's Dome is just over 2,000 meters. And remember we said that as we go up in elevation, barometric pressure is going to go down. So when we are at sea level, our atmospheric pressure is 760 millimeters of mercury, but when you're on the top of Clingman's Dome, it's just 615 millimeters of mercury. So when you're on the top of Clingman's Dome, what's the partial pressure of oxygen? To do this problem, you should have taken 615 millimeters of mercury and multiplied it by 20.9% or by 21%, you could round here, and you should get roughly 129 millimeters of mercury. So you should see as you go up in altitude that the partial pressure of the individual gases will also go down, because at sea level, the partial pressure of oxygen is about 159 millimeters of mercury. So now we can move on to talk about how do gases actually diffuse. And a person we have to thank for our understanding of diffusion of gas is Adolf Fick, who was a German-born physician and physiologist. And what Adolf Fick did was he told us what are the variables that are important that determine gas diffusion. And what he discovered was that the transfer of gas, or the speed at which gas would diffuse into a tissue, was proportional to the area of the tissue, something that's called the diffusion of the coefficient of the gas, the difference in the partial pressures of the gases on the two sides of the tissue, and also that it was inversely proportional to the thickness of the tissue. And those then are the variables that make up our equation for how gases are diffusing across the tissue to go from one location to the next. Now, I don't expect you to be able to go through a calculation using this equation, but I do expect you to be able to tell me how each variable would influence the diffusion of gas. For example, as a tissue thickness increases, you should be able to tell me that that would decrease the diffusion of gas. Whereas if the tissue area increased, you should be able to tell me that that would increase the diffusion speed of a gas across the tissue. As mentioned on the previous slide, the difference in partial pressures between two sides of tissues are going to be some of the driving force to help move or diffuse that gas across a tissue membrane. And we have two tissue membranes we need to move across. We need to move across the tissue membrane of the alveoli in the lungs to move oxygen into the blood. And then we also need to move across the membranes in the tissues that we're perfusing. So for example, our highly active skeletal muscle, in order to get oxygen to the mitochondria. This is a really important figure from your textbook that highlights the partial pressures of both oxygen, which we're trying to move to the tissues, and CO2, which we're trying to move out of the tissues. It's important to point out that the alveolar partial pressure of oxygen is 104, and this is a result of the mixing atmospheric air, with existing alveolar gas along with vapor pressure. That's why that is not just directly 159 millimeters of mercury, because remember, you always have some air that you're breathing out, and so you have a mixture of gas that occurs in the lungs. As that oxygenated air makes its way from the alveoli to the heart, the partial pressure of oxygen goes down to 95 millimeters of mercury, and by the time it gets itself to the tissues, it's down to 40 millimeters of mercury. So it's moving down a pressure gradient to deliver the partial pressure of oxygen to the tissues. A fun fact is the partial pressure of oxygen within the mitochondria is somewhere between 0 and 2 millimeters of mercury, continuing to drive that oxygen all the way down to its final resting place within the cell. Now on the flip side, we have carbon dioxide. And remember, we're consuming oxygen and we're producing carbon dioxide as a byproduct. So that carbon dioxide is being produced in our active tissues as a metabolic byproduct. So the partial pressure of carbon dioxide within our muscular tissues is about 46 millimeters of mercury. It's transported through the venous blood back to the heart, where the partial pressure is roughly 46 millimeters of mercury, and then it makes its way to the circulation of the lung, where it's about 40 millimeters of mercury. So it's also moving down a partial pressure gradient, but you'll notice that that gradient is much smaller than the gradient that's pulling oxygen into our lungs. A really common mistake that I hear students make often is when they're talking about blood flow volumes going to the respiratory system and then blood flow volumes going to the systemic circulation. So in effect, the blood that's leaving the left ventricle versus the blood that's leaving the right ventricle. And the issue here is students often like to tell me that, oh yeah, less blood goes to the respiratory system, more blood goes out to the systemic circulation. That's actually not true. The same volume of blood goes to the systemic circulation as is going to the respiratory system or the lungs with each beat of the heart. The large difference here is what pressure is that blood being ejected with. So the left side of the heart, or the left ventricle that goes out the aorta, is a very high pressure system. So that blood is being ejected at a very high pressure. Whereas the right side of our heart is a much lower pressure system that's sending the blood to our respiratory system, specifically to our lungs, to be oxygenated. Another concept that students often struggle with is, how is blood perfusing the lungs? Well, as you stand upright, our lungs have to deal with gravity. So we tend to perfuse the bottom third of our lungs, or the base of our lungs, more than the apex or the top of our lungs when we're at rest. And when we start exercising and we have changes in pressure, we do a better job of perfusing the whole lung. Still not perfect, but a better job than what we're doing while we're at rest. This is a really nice figure that highlights the ventilation-perfusion ratio that occurs in the lungs. And the top of the lungs, or the apex, is going to be different from the bottom of the lungs, or the base. And we know this because we have differences in blood flow to the top and the bottom of the lungs that we highlighted in the previous slide. So the top of our lungs, the apex of the lung, is underperfused, whereas the base of the lung is overperfused. So if we take a look at the top of the lungs, we're looking at a ventilation of about 0.24 liters per minute and a blood flow of about 0.07 liters per minute, which gives us a ratio of 3.43. So a very large or disproportionate ventilation to perfusion ratio represents a high ventilation relative to blood flow, which is going to result in very poor gas exchange. In contrast, at the base of the lungs, what we find is that we have a ventilation of about 0.82 liters per minute with a blood flow of about 1.29 liters per minute, so that higher blood flow. The ratio here is about 0.64. So a ratio of less than 1 means that blood flow is higher than the ventilation to that specific region. And even though the ratio is less than 1, that's not necessarily indicative of ideal conditions for gas exchange in most cases. Generally, any ratio that's greater than about 0.5 is going to be adequate to meet the gas exchange demands when someone is at rest. So then what happens when we're exercising and we know we have pressure changes in the chest cavity that are going to influence the perfusion of the lungs? Well, during light exercise, what we see is an improvement in perfusion of the entire lung, which then can improve overall gas exchange. Whereas when someone is doing heavy exercise, this may result in a small inequality of that ventilation perfusion ratio. So sometimes you have very minor impairments in gas exchange with very heavy exercise.